Okay, now we're going to talk about parametric versus non-parametric tests. Actually, we're going to focus on the non-parametric test now. Now, a parametric test has a parametric tests have requirements about the nature or shape of the population involved. So there are requirements about distribution. Non-parametric tests, however, do not require that the sample come from populations with normal distributions or any particular distribution. Consequently, non-parametric tests of hypothesis are often called distribution-free tests. So we're not making any assumptions about what the distribution of the underlying population are. Some of the advantages of non-parametric tests are they can be applied to a wider variety of data and situations because of the relaxing of the requirements of knowing the underlying distribution. And you can apply these to categorical data and such as gender or hair color. And some of the disadvantages of non-parametric tests are you lose data a lot, and they're not as sensitive or efficient as their parametric counterparts. So generally, you need stronger evidence in a non-parametric test to get anything that's statistically significant. All right, one of the non-parametric tests that we're going to look at is called the sign test. And the sign test is a non-parametric test that uses plus and minus signs to test to test different claims. So we're going to use either a plus sign or a minus sign to represent something, and we're going to use those signs to test different claims. And the three type of claims that we're going to use the sign test for are claims involving matched pairs. We're going to take a look at an example of that. Claims involving nominal data, uh, and claims about the median of a single population. So uh, here are some things. The objective of the sign test, and we just went through three of the objectives. X, let's take a look at the notation. X is going to be the number of times, excuse me, X is going to be the number of times that the less frequent sign occurs. So remember, we're using plus or minus signs. X is going to represent the frequency of the less frequent sign, either plus or minus. Now, N is the total number of signs. So N is the total number of signs, and X is the frequency of the least frequent sign. Now, for a small sample, N less than 25, we're going to let the test statistic be that value X that we found. But for a large sample greater than 25, we're going to calculate this z-score using X, and we're going to actually use the z-distribution instead. Now, the critical values, well, the critical values are found in A7, or if the sample size is greater than 25, you can also remember we would use the z, so they would be found in A2. But what we're going to do is we're going to use technology. We're going to use the TI-83 calculator because this statistic actually is binomial by nature. If you consider pluses and minuses to be successes and failures, and n would be the total number of observations, or the total number of trials. All right, so we're going to use software, and here is an example. And here is actually the procedure for conducting the sign test on the TI-83 to get a p-value. All right, so the first thing we want to do is we actually want to look at these differences and assign signs to them. So let's take a look at example 9. Listed below are the ages of actresses and actors at the time that they won the Oscar. The data are paired according to the year that they won. Use a zero point zero 0.05 significance level to test the claim that there is no difference between the ages of the best actress and the age of the best actor at the time that the awards were presented. So what we actually want to do is we want to find the sign of each of these differences. So we want to know the difference between the best actor and the best actress's age. All right, so let's see. The best actor in this first column here is 62 and the best actress is 28. So the difference between the best actor and the best actress at the time they won. Here, we're going to put the signs in the bottom row. And this difference here is positive. The first difference is positive. Oops. So we're going to put the signs here, sign. And this first difference between best actor and best actress is positive because the best actor's age is larger than the best actress's age. The second one, the best actor versus best actress, 41 minus 32 is also positive. 52 minus 27 is also positive. 41 minus 27 is also positive. 34 minus 26 is also positive. 40 minus 24 is also positive. 56 minus 25 is positive. 41 minus 29 is positive. 39 minus 41, that's going to be negative. So this is our first negative sign. 49 minus 40 will be positive. 48 minus 27 is positive. 56 minus 42 is positive. 42 minus 33 is positive. 62 minus 21 is positive. And 29 minus 35, that one is negative. All right, so now we can identify all of our different values that we need. One value is n. N is the total number of signs, and I have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 different years. So n is equal to 15, and x, remember, was the frequency of the least frequent sign, and the least frequent sign here is definitely negative. So x is equal to 2 because there are two negatives, negative differences. All right, so we've identified n and x. And now all we have to do is use this information in the TI-83 to come up with the p-value. And the null hypothesis here is that there is no difference. So we're using a 0.05 significance level to test the claim that there is no difference between the ages of best actor and best actress. And that means that alpha is equal to 0.05. That's the significance level. The null hypothesis is that there's no difference. No difference. And the alternative hypothesis is that there is a difference. All right, so now we're going to find a p-value and compare it to our level of significance so that we can come up with a conclusion. So this is how we do it in the TI-83. It says what we have to do is hit second first and vars to get to the distributions, and we're going to be using the binomial distribution with n, p, and x. And for p, we're going to use 0.5. All right, so because it says right here where n is the total number of plus and minus signs, that's n, 0.5 for p, and the number of the less frequent sign is x. So we have x is equal to 2. P, we're going to use 0.5. All right, so let's go ahead and plug all that information into the TI. All right, so here we have it. We're going to go to second vars to get to the distributions, and we're doing the binomial distribution. So we go down to binom CDF, like it says here, the binom CDF, and we press enter. And for the parameters, we're going to plug in n, which is 15, 1, 5. Then we're going to put the comma, p, which it says to use 0.5, comma, and then x. Well, x we found to be 2, so x is 2, and then close the parenthesis, and when I press enter, it's going to give me the p-value for this hypothesis test. So the p-value is 0.004. So there I have my p-value, is 0.004 p-value. And because this p-value is less than alpha, which is 0.05, we're going to reject the null hypothesis. So we reject the HO. We reject the null hypothesis. And the null hypothesis is there's no difference. We're rejecting that. So we're rejecting it in favor of the alternative hypothesis, which says that there probably is a difference between the ages of the best actor and best actress in the year that they won. So there is a difference between the numbers on the bottom and the numbers on the top.